Hello and welcome to the lecture on Chapter 12 from Astronomy Today. The topic of Chapter 12 is the planet Saturn. Last week, we talked about the planet Jupiter, so this is our second week talking about gas giants. Saturn and Jupiter have a lot in common, but obviously some important differences, as we can tell because of course Saturn has its famous rings. So let's talk about what are the physical differences, why should these planets be so similar, yet have these key differences. And we'll talk about Saturn's moons and a few other interesting topics. Let's summarize those topics. So first of all, we want to talk about the orbital and physical properties of Saturn, as we do for all of the planets in the solar system. We want to start from the outside in and talk about the atmosphere of Saturn. What's up with its clouds? Why are the clouds less colorful on Saturn as compared to Jupiter? Then we want to talk about its interior and the formation of its magnetosphere, which is this magnetic field. We want to talk about its spectacular ring system. That's really the thing that makes Saturn stand out. We will talk about its moons because, like all the Jovian planets, Saturn has a lot of moons. Of course, Jupiter has 4 very famous moons. Saturn has a few famous moons as well. And we'll do a little discovery about dancing among Saturn's moons. All right, so here are the details, breaking down the numbers. Saturn has a mass of 5.7 times 10 to the 26 kilograms. Okay, so quite a bit more massive than Earth at 10 to the 24 kilograms. It has a radius of 60,000 kilometers, so about 10 times the radius of Earth, which is 5,600 kilometers. And it has a density of only 700 kilograms per cubic meter, right? That's less dense than water because water has a density of 1,000 kilograms per cubic meter. So it's only 70% as dense as water. It is the least dense planet in the solar system, all right, by far, and is the only planet with a density less than water. Jupiter, much less dense than the rocky terrestrial planets, still has a density greater than water because all that highly compressed gas in its interior, as well as its rocky core, well, those all lead to a greater total density. Not so with Saturn. Well, what about its rotation? Well, it has rapid and differential rotation. We saw the same thing with Jupiter, all right? In fact, all the Jovian worlds, including Uranus and Neptune, all have very fast rotation around their axes, okay? And it is enough to significantly flatten Saturn because since its upper surfaces are so gaseous, there's a noticeable elongation. It's wider along the rotational equator than it is around the poles, okay? It really stretched out because it's spinning so fast. Its rings are very prominent, right? You could see them with rudimentary telescopes. They're right there. Galileo saw them. He thought they were ears on the planet, or something like that at least. But the point is that they're so easily visible. They're so dramatically bright and highly reflective. All right. So here are views of the rings from Earth. All right, which obviously change as Saturn orbits the Sun, right? Because the orientation changes. Okay. So here are all different views of Saturn throughout the year, right, as viewed from Earth. Here is a 2-scale orbit of Earth. We're much closer to the Sun than Saturn is. We've gone out to a very great distance to get to Saturn's orbit, all right? And we can see that the orbit takes many years, Earth years, to get all the way around, right, all the way around the Sun for Saturn, going from 2017, all right, over here, but starting in 2003, you can see, right, or actually starting in 1995, to get all the way out in 2017 there, many years, okay? But despite that, we see that there is a change in the orientation, and that's because of the tilt. See, Saturn has an axial tilt. Relative to the ecliptic plane, that would be the angle theta of the axial tilt, much like Earth's axial tilt, right? And like all axial tilts, they remain fixed relative to the background stars. So that means sometimes the North Pole of Saturn is tilted towards the Sun, sometimes it's tilted away, like over here, all right? And that just changes the view of the rings, right? Among other things, obviously, right? Okay. So what about Saturn's atmosphere? Well, its atmosphere, all right, shows zones and band structures. Where did we see that before? Just like Jupiter, okay? So that's a similarity between the two planets. But the coloration is much more subdued than Jupiter's, okay? The atmosphere is mostly molecular hydrogen. When we talk about molecular hydrogen, that's H2, so it's the diatomic molecule, 2 hydrogen. It also has some helium, good deal of methane, and ammonia, all right, common ingredients out in the outer solar system. However, the helium fraction is much less than Jupiter's. So the amount of helium on Saturn is much less than the amount of helium on Jupiter. okay? So why is there missing helium on Saturn? Well, we'll talk about that briefly, okay? All right, so that's some key characteristics, much more subdued colors, very similar building blocks, but less helium as compared to Jupiter, all right? This true color image shows the delicate coloration of the cloud patterns on Saturn, right? So we can see that there is some bands, right? If you follow along this arrow, you can see bands, but they're subdued, right? They're all kind of flattened out, almost like they're all behind a screen, okay? So what else can we say about Saturn's atmosphere? Well, so it's similar to Jupiter's. I think we've got that point across, except the pressure is lower, all right? So it's significantly lower pressure because there's significantly less gravitational attraction. Saturn is has a much lower mass than Jupiter. There's much less gravity. That's condensing the cloud layers less, all right? There are 3 cloud layers, and the cloud layers are thicker than Jupiter's. So what happens then is because the cloud layers are so thick, including that top layer, that's most of what we see. That's why it looks like the bands of Jupiter are behind a screen, because unlike, the bands of Saturn are behind a screen, because unlike on Jupiter, there is a thick upper cloud layer. All the clouds are thick. On Jupiter, they're so compressed together that the clouds are highly pressurized, all packed on top of each other. There's no diffuse upper clouds like there is in Saturn, okay? And it all comes down to less mass, less gravity. Because again, the mass on Saturn is much less than the mass on Jupiter. Even though they're somewhat comparable in size, the 2 planets, Jupiter is much denser. It's been packed down by gravity significantly more. All right, here is just a view of the different layers of Saturn's atmosphere with the stratosphere, the haze that makes the subdued colors in the troposphere. We've got a cloud layer of ammonia ice. We've got a cloud layer of ammonium hydrosulfide ice. And below that, we have a cloud layer of water ice. Okay? And we can see that we have temperature variations. It gets warmer and warmer as we go down into the clouds, right? Approaching, almost Earth-like temperatures, but higher pressure. Right, we have that the pressure gets up to about 10 Earth pressures by the time the temperatures get reasonably high. Up here, where there's 1 Earth pressure, the temperature is significantly lower, right? But not as dramatic as Jupiter, okay? And there's a little bit of a temperature spike as we go up into the stratosphere due to the absorption of high energy photons. Just like with any planet's atmosphere, it's becoming less pronounced as we get further out in the solar system because we're just getting further and further from the sun. So those high energy ultraviolet rays, those high energy X-rays that come from the sun, there's just fewer and fewer of them per square meter as we get further from the sun. So the structure in Saturn's clouds can be seen more clearly in this false color image, right? So we can look at those layers if we can kind of get out the haze, right? If we can filter out that upper haze. So we can, kind of look at the infrared signature and then recolor it in the visible spectrum. Then we can see what's going on underneath the upper haze, all right? Now, what about the wind, right? Well, the wind patterns on Saturn are similar to those on Jupiter, right? There's zonal flow, right? There's no one velocity for the surface because although the whole planet and its core rotates at a particular rate, very rapid, because of the high velocity winds, we have, significant variation in the actual speed of the surface of the planet, right? So we see here that the eastward wind speed on the equator is very great, so it's moving faster. So that means that the gas in the atmosphere of Saturn, as we get closer to the poles, can't keep up with the fast-moving gas at the equator. So there's be constantly shearing between the slower-moving gas near the poles and the fast-moving gas at the equator. Right? So there's always shearing going on that drives storms, that creates that differential approach, and it creates the bands that we see. Okay. There are Jupiter-style spots on Saturn, but they are rare, right? They don't form often, and they quickly dissipate if they do. That probably has everything to do with the much less energy because Saturn is cooler, so the temperature of Saturn is less than the temperature of Jupiter. We'll mention that again. And so we have a planet that's less dense, and it's cooler, so there's less energy to drive those giant storms that will continue for so long on Jupiter. All right, so storms happen on Saturn, but they dissipate more quickly. Okay, this image here, right, that's a beautiful image, shows a huge storm on Saturn. It is expected to last at least 2 years, And smaller storms dissipate more quickly due to extreme high wind speeds. Right? But this storm will continue in one form or another for a couple of Earth years, not Saturn years, by the way. Okay, so now let's drop down out of the atmosphere and dive down into the interior of the planet and talk about where the magnetosphere comes from and the magnetosphere itself. So here is the internal structure, right? Very similar to Jupiter. So you can absolutely group Saturn and Jupiter. If you haven't noticed, right, the comparison keeps being made. And I mentioned that grouping because when we talk about Uranus and Neptune, we'll talk about how we can kind of group them together as well, and they have separate characteristics from Saturn and Jupiter. Okay, but Saturn and Jupiter, very, very similar interior structures. We have molecular hydrogen being the dominant gas in the upper layers of the atmosphere. All right, we have a depth of about 250 kilometers, temperature 250 Kelvin. Okay, and pressure 10 Earth atmospheres. Okay, all right, so there's our numbers. By the way, 250 Kelvin is still below 0 degrees Celsius, so we're still talking quite cold here. All right. 273 Kelvin is 0. So this isn't unbelievably cold, but it's certainly cold. As we move out of the layer of molecular hydrogen, then we move into the metallic hydrogen layer. This is where hydrogen has been compressed into a solid, behaving like a metal. This is at a depth of 30,000 kilometers. Remember, the whole radius was 60,000, so it's halfway down. It has a temperature of 8,000 Kelvin, so incredibly hot, and a pressure of 3 million Earth atmospheres. Okay, that's how much pressure you need to take hydrogen, which doesn't want to become a solid, and actually compress it into a solid. As we move further down, we get to a depth of 45,000 kilometers, and the temperature reaches 10,000 Kelvin at 10 million atmospheres. All right, what's going on down there? Well, we've got the ice and rock that has sunk to the core, right, compressed to very, very high pressure. All right, and that's basically what's going on in the very core. Ice and rock surrounded by a sheath of metallic hydrogen. So Saturn also radiates more energy than it gets. And when we say also, what are we comparing to? Yep, you guessed it, just like Jupiter. Okay. For Jupiter, the primary theory suggesting why Jupiter outputs more energy than it gets is because Jupiter is still cooling. You know, some 4.5 billion years later, since there was so much energy that went into the formation of the largest planet in the solar system, it is gradually cooling. All right. Now, is that what's going on with Saturn? Well, not just because of cooling. All right. Now, there might be some cooling in terms of Saturn, but Saturn is already very cool. So what's driving the heat output from Saturn? Well, it's basically that it's condensing. The planet is still collapsing in a sense. Helium and hydrogen are not well mixed in Saturn, and that's probably due to the fact that it's less massive, so gravity hasn't had that chance to mix them as much. That means that the helium tends to, since it's able to be in clusters of pure helium, condense into droplets. There's a greater likelihood of condensation of helium. And when that happens, when the helium condenses together, this is very cool helium. Obviously, helium at Earth atmospheric temperatures would never condense because helium is a very light gas. You think of a helium balloon, that helium wants to escape the balloon, and so there's no chance of helium rain on Earth. But you have to realize Saturn is so much cooler, so it's a very cold planet, and so this condensing helium then falls as rain. All right, and that process is so pronounced, and there was so much helium over the billions of years. There has been so much helium in the atmosphere of Saturn that process has continued to allow gravitational energy to then produce heat. Because that falling rain, that energy has to go somewhere. You've got the kinetic energy of the falling rain. When that rain, that's the helium rain, the condensed helium. When the helium then sinks into the deeper layers of the planet, right? Then that basically rubs against other molecules, creating friction. That heat has to go somewhere through random processes. That heat then will re-reach the surface of the planet and then radiate out into space as infrared radiation. And that's how we look and we say, oh, look, there's more energy coming out of the planet than going in. And the dominant theory it's because of that helium rain. Okay, gravitational energy becoming heat. Now, will eventually all the helium condense? Yes, right? But at this point, it's still gradually condensing, and we can tell that this theory makes sense because if we look at that composition of the atmosphere, we see very little helium because the helium condensed and now it's in the core. That's why Saturn's atmosphere is lacking helium. All right, so also, like Jupiter, Saturn has a very strong magnetic field. Now, to be fair, all the Jovian planets, all the big gas planets have strong magnetic fields, okay? But it's only 5% as strong as Jupiter's. So you might be like, really? That's considered strong? Well, Jupiter's is so unbelievably strong. I mean, Jupiter's magnetosphere is larger than the sun. It's such a huge influence. Saturn's is large compared to the terrestrial planets, certainly much larger than Earth's magnetosphere, but it's just nowhere. It's dwarfed by the sheer size of Jupiter's magnetosphere. Okay. The magnetic field, just like Earth's magnetic field, creates auroras. Saturn's magnetic field does. Auroras is because of the redirection, and we think of this, as the magnetic field going towards the South Pole up here, the field lines pointing in that direction. All right, the north magnetic South Pole. Then those field lines coming up there, and you might be like, yeah, maybe that's drawn at the north. But just I'm assuming it's like Earth, where the geographic North Pole is actually a magnetic South Pole. I'm not sure if that's the case of Saturn. Those tend to vary between planets. But regardless, there's a pole up here, and there's magnetic field lines. And so then when we have charged particles in the solar system, like electrons, they get directed along those magnetic field lines. And so then those charged particles then release energy in the form of visible light. And that's what we see at the auroras. Right? You can see aurora down here. Right, so it's all about charged particles following the field lines along helical paths. Okay? So what about those spectacular rings? Well, Saturn has an extraordinarily large and complex ring system, which was visible even to the first telescopes. As I mentioned, very first telescopes, Galileo, one of the first telescopes, saw the rings. They were that visible, right? So we can see, even at very, very rudimentary telescopes, clearly the planet has an unusual shape with large lobes. As we improve the resolution of the telescope, we can clearly see that there's spacing in those lobes. And then eventually, when we get nice images, we can see that really it looks like a ring. The rings are incredibly thin. They have very little thickness to them, but they're very wide, okay? So there are details to the rings. There's just not one ring, there are many concentric rings. So there is the C ring, which of course is composed of many concentric rings, but it's different in structure to the B ring. Then there's a large gap called the Cassini division. Then there is the A ring, and within the A ring, there is the NK gap, okay? So these are just the terms given to the different parts of Saturn's rings. Okay, so ring particles range in size from fractions of a millimeter, so a tiny little piece of dust, to tens of meters. There are chunks of ice within the rings that are asteroid size, but they're more similar in composition to a comet because they're icy. All right, the ring is mostly water ice, essentially snowballs. Okay, so that's the thing here. It's not carbon dioxide ice. It's water ice. It's not mostly ammonia or mostly methane. It is mostly H2O, interestingly, okay? And the thing is, the reason that Saturn's rings show up so dramatically is because they are so reflective. That water ice has not had time to get covered in darker molecules that would lower the reflectivity. Instead, we have very pure ice that is still very reflective. I say still because scientists really suspect that Saturn's rings are transient. They don't last forever. The rings that we see being so bright and reflective are probably bright and reflective like that for a few tens of thousands of years. Then they'll gradually get dirtier. And what happens is that the rings are probably refreshed due to events such as tearing apart a comet due to the gravitational pull of the planet Saturn. And that brings us nicely into this question of why rings? Where do rings come from in the first place? Why do these large planets have rings? Well, the rings exist because they're too close to the planet to form a moon. Okay, so certainly these planets like Saturn and Jupiter are capable of capturing comets, kind of having them become moons. But if that captured path of the comet is too close, then what happens? It gets torn apart. Even something like the size of Pluto would gradually get torn apart if it was placed in an orbit that was as close to Saturn as Saturn's rings are. What happens is the tidal forces are so great at that distance that they're greater than the internal strength of the comet or planetoid or whatever it is that then becomes a ring. So the ring is just the byproduct of these tidal forces tearing apart comets, asteroids, and dwarf planets. All right, that's where the rings come from. And that point, that limit of being too close, is called the Roche limit. All right, that's the distance to a planet that a moon cannot exist. So anything less than the Roche limit, no moons. All right, so less than means no moons because they would be torn apart. All right, so if you put a moon inside the Roche limit, it gets torn apart from what? Tidal forces. Okay, so the closest distance that the moon can survive is called the Roche limit. There it is. Okay, ring systems are all inside this limit. So we compare all the gas planets, because yes, it's worth repeating, Jupiter, Saturn, Uranus, and Neptune all have rings, and they're all inside of that approximate Roche limit for the respective planet. Okay? And these values aren't the same for each planet because it depends on the size of the planet, but they're all dependent on the radius of the planet. Okay? All right. And Voyager, a probe that went out into the outer solar system, showed Saturn's rings to be more complex than originally thought. Okay? That's where we first realized that they had the complex differentiation, such as the Cassini division and the shape of the B ring and so on. All right? Note the large number of tiny ringlets visible. And to show you the sheer size of the rings, we can see they are many times longer than the diameter of Earth. But they're only about a couple thousand meters thick. They're incredibly, incredibly thin. At their thickest, they're about 10 kilometers, so about 10,000 meters thick. Okay, but often they're just maybe 1,000 meters thick, the rings. So thin. Okay, this backlit view shows the fainter F and G and E rings. So you can see there are further out rings that are fainter. All right, and we can see the planet Enceladus as it goes through one of the rings, as it passes through the E ring. Interesting thing about Enceladus is Enceladus actually spews water into space because it has these geysers that break up out of its frozen surface. And of course, then some of those molecules certainly then get trapped in the ring that is its orbit. Okay? Voyager also found radial spikes that formed and then dissipated, and this probably happens frequently. All right, so there's probably lots of these these phenomenons of just gradual changes in the ring. That'd be just due to these random fluctuations. Then gravity then pulls together parts of the ring, but then they'll flatten back out over time. Okay. Other edges and divisions in the rings are also the results of resonance. Remember, resonance is the idea of having orbits that are even multiples of each other. So if you have two objects that are in resonant orbit, then they're going to line up every second orbit or every third orbit. And that lining up of resonant orbits means that things get pulled every time they line up. Okay? And we also have shepherd moons that define the outer edges of the A ring through gravitational interactions. So there's these small moons within the rings, and these are moons that are thought to not last forever. These moons themselves will only be around for tens or hundred thousands of years and will, as we mentioned, eventually get pulled apart by tidal forces. But for now, being a larger object with a lot more inertia and gravitational force, they actually shape the ring around them. And the strangest ring is the outermost, the F ring, as it appears to have braids and kinks, right? Almost like, solar flares, odd effects, probably just due to very, very small gravitational phenomenon, due to the fact that these are small particles, not a lot of gravitational pull from the planet. So any tiny perturbation, any tiny little pull can have probably these very interesting effects. Okay? So the details of the formation are unknown. Again, it's a modern theory. This is current science, speculating on the idea that the rings don't last that long. But it's really the dominant theory because otherwise there's no good explanation about why they would be so reflective, right? They can't last that long if they're that reflective. They must get formed and reformed. And we just happen to see the results of rather recent rings. Okay, they're probably too active to have lasted since the birth of the solar system, all right? Not all rings may be the same age, and they either must be continually replenished, right, which is kind of the idea I keep coming back to, or are the results of a catastrophic event, right? So maybe just some point, what used to be in another, Pluto-sized planet got pulled into Saturn, right? And the ring came from that. Okay, so enough about the rings. Saturn also has a huge system of moons. And Saturn's many moons, and most of the moons are not within the rings, by the way. There are a few, the Shepherd moons, and Enceladus is way out there on the edge of the F ring, but most of the moons are further out, further away from Saturn, okay? So many moons appear to be made of water ice. That's the most common type. That would be like Callisto, the moon of Jupiter, right? Basically a muddy ice ball, right? In addition to the small moons, Saturn does have a few large moons, okay? Well, medium-sized moons and one large moon. Okay, so there are 6 medium-sized moons: Mimas, Enceladus, Tethys, Dione, Rhea, and Iapetus, or Iapetus. Iapetus, that's it, Iapetus. And the one large moon, Titan, which is a good name for the large moon, which almost is as large as Jupiter's Ganymede. So Titan is the second biggest moon, because you remember Ganymede is the only moon in the solar system that's larger than a planet. Ganymede is bigger than Mercury. Titan is the second biggest moon in the solar system. Titan is huge, okay? Titan is a very fascinating moon. It has been known for many years to have an atmosphere thicker and denser than Earth's. Right? So it actually has an atmosphere. It is the only moon with an atmosphere in the entire solar system. Okay, it's mostly nitrogen and argon. All right, it makes the surface impossible to see. You have to land on the surface to see it. And the upper picture at the right was taken only 4,000 kilometers away, right? But still, it's totally, just totally opaque. It's such a thick atmosphere. It's not as thick and dense as Venus's atmosphere, but it is denser than Earth's. Is it an atmosphere that we could breathe? Well, nitrogen is a good sign. That's most of our atmosphere is mostly composed of nitrogen. But no, we cannot breathe the atmosphere of of Titan. And there's not a lot of liquid water on Titan, or any. In fact, the only liquids on Titan are going to be methane and ammonia. And we think that there are, like basically storms of methane and ammonia, and lakes and rivers, and erosion caused by methane and ammonia rain. Okay. So trace chemicals in Titan's atmosphere make it chemically complex. So we can look at a altitude versus temperature graph of the atmosphere of Titan, since it has an atmosphere, right? We wouldn't do this for any other moon because no other moons have atmosphere. And we can see that there is a ultraviolet absorbing haze that we can't really see through. Underneath that, we have an ultraviolet optical haze. Then we have a main haze. We have an aerosol haze. So these are just particles that are so small that they never sink back down to the ground. That's what an aerosol means. There's not enough gravitational pull to pull it back down. And then finally, underneath all that haze, we have real, clouds, methane clouds, and methane rain. All right. So there actually is what would look like a functioning atmosphere underneath there, with clouds and storms and all that, but at a much cooler temperatures. Because we don't have methane rain here on Earth, because methane is going to be a gas, but the much cooler. Look at the temperature here, right? The surface temperature around 100 Kelvin. That's about 170 degrees cooler than the surface of Earth, right? Freezing cold, but fine for having liquid methane, okay? All right, some surface features on Titan are visible in this Cassini infrared image. So actually looking through the cloud layer by using the non-visible part of the spectrum, using the infrared, right? And then using artificial color to show some of the features, right? And we can see what looks like a crater, lots of examples of erosion, okay? We can see drainage channels, so clearly that methane rain comes down, has an effect on the landscape. The Huygens spacecraft have landed on Titan, all right, and return images directly from the surface. All right, so we can see rocks, almost looks like Mars, right? But there are lots of interesting surface features on this incredibly fascinating moon. Okay. As far as the inside of Titan, right, based on measurements made by Cassini, as a flyby mission past Titan, and that Huygens probe that landed on the surface, this is the current best understanding as to what the interior of Titan looks like. Obviously, this is evolving science, right? We're just kind of modeling on this as best we can, because we know the mass of Titan based on its dynamic behavior in orbit, and then we can reason out what it must be made of. Okay, so we think that it has a rocky ice core. It has high pressure ice outside of that, right? Which has enough energy that's probably very easily liquefied. Then we have liquid water sitting on top of that, okay, by mixed of dirt, almost like a huge ocean. Then we have near surface ice, and then finally a rocky surface. Okay. And as far as dancing among Saturn's moons, well, we did that just recently with the Cassini spacecraft, which has now finished its mission. But and in finishing its mission, it was actually allowed to crash into the atmosphere of Saturn. being completely done, no space junk. But before it did that, the Cassini spacecraft used multiple gravitational slingshots to make multiple close passes around Saturn's moons. Precise orbits are decided on the fly, right? So they're always doing calculations. These are very, very complex phenomena. Imagine bringing a spacecraft in at 30,000 miles per hour, flying by Saturn, but then getting pulled back in by the combined gravitational pull of Saturn, and then doing a quick flyby by Titan, which can then pick up some more velocity and then fly by again, using very little fuel, just a little bit of fuel to readjust, because there's how much fuel can you take with you on a many year long mission? Never enough. And so we're just using these little gravitational tugs to make these decisions about how the spacecraft is going to go around. And the mission was constantly changing. There's always decisions about where they're going to fly by another moon or not, and what data could they take. For example, they flew past that Enceladus moon that I mentioned a while back, got some incredibly interesting data, but then never flew back again because they weren't prepared to take more data. So that's going to be left for decades from now for future missions, because just the time to get to Saturn takes about 10 years. Maybe that number is coming down, maybe to 7 in the future, but still many years just to even get there. All right, but we can appreciate more than just Titan. There are other of Saturn's mid-sized moons, or this collection of mid-sized moons. Many of them have interesting stories in themselves. Iapetus has a huge crater that almost tore the planet across. It has an equatorial ridge due to probably cooling, kind of like the cooling that we saw on Mercury. We have Mimas that also has a huge crater and kind of looks like the Death Star. We have Tethys and Dione and Rhea, which are all large planets are large moons in their own sense. Very much, kind of like Earth's moon, rocky, with lots of craters left over from the age of bombardment. And then finally, we have Enceladus, which is volcanically active, but not with lava or methane ammonia or sulfur or anything like that. It's volcanically active with H2O. So it has huge geysers of water that break up out of the surface. Enceladus is a lot like Europa, which was the icy capped water moon, I don't want to say planet, but water moon of Jupiter. Well, Enceladus is a smaller version of Europa, and we think could harbor life in the subsurface ocean underneath these huge ice sheets on its surface. All right. So Mimas, Enceladus, Tethys, Dione, and Rhea all orbit between 3 and 9 planetary radii from Saturn and are all tidally locked. This means they have leading and trailing surfaces. Right? So they have one face that faces towards the planet like our moon does, and a face that always faces away from the planet. Okay? So that's just like our moon is tidally locked to Earth. Iapetus orbits 59 radii away and is also tidally locked. Right? So Iapetus is much further away than Mimas, Enceladus, Tethys, Dione, and Rhea. Okay? The surface of Enceladus seems oddly youthful, all right, because it's probably constantly being refreshed, right? Not nearly as many craters. We have a section of craters, but we have many sections where the craters have been erased because there's constantly, as I said, geysers. These ice sheets are probably almost acting like plate tectonics. They're sliding relative to each other. Here are these geysers spewing into space, shown by Cassini, all right? And the masses of the small moons are not well known, all right? 2 of them share a single orbit, for example, which almost seems impossible, but certainly is the case, right? Here we have orbits swapping, all right? And there's so many. There's about 50 of these small moons with so much interesting data that continually be collected by scientists, all right? And there are 2 more moons that are at the Lagrange points of Tethys. Because anytime you have 2 gravitational bodies, like say Earth and our moon, there are points where you can put another satellite, and that other satellite will move with the original 2 gravitational bodies. These are called Lagrange points. They're kind of balance points of gravitational tugging. And we see that sometimes we can end up with another moon at the Lagrange point between a planet and its moon. All right, so Telesto and Calypso are at the Lagrange points of Tethys and Saturn. Okay, and again, you can think of the Lagrange point as a gravitational balance point, right? Where the tug of Tethys, which is much closer, and the tug of Saturn, which is massive but further away, because this is not to scale, those tugs cancel out, and then you're able to have another moon at rest to both Saturn and Tethys, right? So that means that Tethys and Telesto and Calypso, they all move together, right? Very cool. All right, so now let's summarize all this information, okay? So Saturn, like Jupiter, rotates differentially and is significantly flattened because it's spinning so quickly, right? And that low density stretches out in the middle, all right? So, so it'd be like stretched out in the middle, right? Because of that rotation. Saturn's weather patterns are in some ways similar to Jupiter's, right? The bands, but there are far fewer storms, much cooler, less energy, okay? All right, Saturn generates its own heat through the compression of helium raindrops, okay? That's why more energy comes out than goes in. Saturn has a large magnetic field and extensive magnetosphere, okay, like all the Jovian planets. Saturn's most prominent feature is its rings, right? That's what it's known for, which are in its equatorial plane, okay? The rings have considerable gross and fine structure with segments and gaps. Their particles are icy and grain to boulder sized. The interactions with the medium and small moons determine the ring structure, and the rings are entirely within the Roche limit, all right? Because the Roche limit is what makes it so there's no moons within there, at least no long-lasting moons, where larger bodies would be torn apart by tidal forces. Titan, right, which is probably was Saturn's most famous moon, is the second largest moon in the solar system. Titan has an extremely thick atmosphere, and little is known about its surface or interior. The medium-sized moons are rock and water ice. Their terrains vary, all right? And these moons are tidally locked to Saturn. And you might just be wondering yourself, why did I say Titan used to be the most famous? Because now it's really Enceladus. Enceladus has become so popular in the scientific community because of its potential for harboring life like Europa. And it seems to be even more promising because its geysers are more active than those of Europa, all right? So it's become quite interesting. But I guess it shouldn't completely overshadow Titan, the only moon in the solar system with atmosphere. But anyway, several of the small moons share orbits, right? Such as having the Lagrange points, and either with each other or with a larger moon. All right, so that concludes our lecture on Saturn. I hope it's been a lot of fun to talk about this famous planet, and you've enjoyed this topic. Thank you so much for watching.